Network Formation Games and the Potential Function Method by Professor Eva Tardish and Tom Wexler. Large computer networks such as the Internet are built, operated, and used by a large number of diverse and competitive entities. In light of these competing forces, it is surprising how efficient these networks are, an exciting challenge in the area of algorithmic game theory is to understand the success of these networks in game theoretical terms. What principles of interaction lead selfish participants to form such efficient networks? In this chapter, we present a number of network formation games. We focus on simple games that have been analyzed in terms of the efficiency loss that results from selfishness. We also highlight a fundamental technique used in analyzing inefficiency in many games, the potential function method. Introduction. The design and the operation of many large computer networks, such as the Internet, are carried out by a large number of independent service providers, which are autonomous systems, all of whom seek to selfishly optimize the quality and cost of their own operation. Game theory provides a natural framework for modeling such selfish interests and the networks they generate. These models in turn facilitate a quantitative study of the trade-off between efficiency and stability in network formation. In this chapter, we consider a range of simple network formation games that model distinct ways in which selfish agents might create and evaluate networks. All of the models we present aim to capture two competing issues. Players want to minimize the expenses they incur in building a network, but at the same time seek to ensure that this network provides them with a high quality of service. There are many measures by which players might evaluate the quality of a network. In this chapter, we focus primarily on measures of distance and connectivity rather than measures based on congestion effects, as it done previously. We also assume that players have financial considerations. In the following sections, players seek to minimize the construction costs of the networks they create. We look at a game with a more sophisticated financial aspect. Players represent service providers who set prices for users and seek to maximize their profit, namely their income from users minus the cost of providing the service. For all of the games we consider, we use Nash equilibrium as the solution concept and refer to networks corresponding to these equilibria as being stable. The models we focus on involve players who can unilaterally build edges, and thus the Nash equilibrium solution concept is appropriate. To evaluate the overall quality of a network, we consider the social cost, or the sum of all players' costs. We refer to the networks that optimize social cost as optimal or socially efficient. The main goal of this chapter is to better understand the quantitative trade off between networks that are stable and those that are socially efficient. More precisely, we are interested in bounding the price of anarchy and the price of stability, as defined in Chapter 17. The models we consider in this chapter are network formation games in which these measures are provably small. In section 19.2, we consider a local connection game where the nodes of the graph are players who pay for the edges that connect them directly to other nodes, incident edges. In selecting a strategy, players face two conflicting desires: to pay as little as possible and to have short paths to all other nodes. Our goal here is to bound the efficiency loss resulting from stability. Such connection games have been extensively studied in the economics literature. See Jackson 2006 for a survey to model social network formation using edges to represent social relations. The local connection game can also be thought of as a simple model for the way subnetworks connect in computer networks by establishing peering points, or as modeling the formation of subnetworks in overlay systems such as P2P, peer-to-peer networks connecting users to each other for downloading files. We will use a model in which players can form edges to a neighbor unilaterally, and will use Nash equilibrium as our solution concept. This differs from much of the literature in economics, where it is typically assumed that an edge between two players needs the consent or contribution from both players, and where the notion of pairwise stability is used instead of a Nash equilibrium. We will discuss how the results extend to models using pairwise stable equilibria in the notes. The model we examined was introduced by Fabricant et al. 2003 and represents the first quantitative effort to understand the efficiency laws of stable networks. In this game, a single parameter alpha represents the cost of building any one edge. Each player, represented by a node, perceives the quality of the network as the sum of distances to all other nodes. Players aim to minimize a cost function that combines both network quality and building costs. They attempt to minimize the building costs they incur, and the distances to all other players. Thus, players use alpha as a trade-off parameter between their two objectives. This is perhaps the simplest way to model this type of trade-off, while the simplicity of this game makes it easy to evaluate. Such a stylized model ignores a number of issues, such as varying costs and possible congestion effects. In section 19.5.1, we discuss the related models that address some of these issues. In section 19.3, we study a very different and also quite simple model of network design introduced by Anshelevich et al. 2004 called the global connection game. Whereas players in the game of section 9.2 only make local choices which other nodes to link to, players in this game make global decisions in that they may build edges throughout the network. Unlike the local connection game, this global game attempts to model players who actually build and maintain large-scale shared networks. This model also allows for greater heterogeneity in the underlying graph. In the global connection game, a player is not associated with an individual node of the networks, but instead has certain global connectivity goals. To achieve these goals, a player may contribute money to any set of edges in the network. As before, we view connectivity as the primary measure of quality. However, players do not desire uniform connectivity. Instead, each player has a subset of nodes that it needs to connect, and aims to do so as cheaply as possible. Furthermore, unlike in the local game, players are not concerned with distance and simply want to connect their terminals. As in the previous model, players are sensitive to costs. Edge E has a cost CE greater than or equal to 0, and players who use E share this cost. In particular, we focus on a fair sharing rule. All players using an edge must share its cost evenly. This natural cost sharing scheme can be derived from the Shapley value and has many nice properties. We also examine other cost sharing games and discuss the role of fair sharing in the price of stability results. A key technique used in this section is the potential function method. This method has emerged as a general technique in understanding the quality of equilibria. We review this technique in detail in section 19.3.2. While this technique provides results only regarding the price of stability, It is interesting to note that many of the currently known price of anarchy results, e.g., most of the results in part 3 of this book, are for potential games. In section 9.4, we consider another potential game, a facility location game with a more sophisticated cost model. In the previous two sections, players simply minimized their costs. Here, edges still have costs, but players also selected prices for users so as to maximize net income, price charged minus the cost paid. We again consider a very simplified model in which players play facilities to serve clients, thereby forming a network between the providers and the clients. We show that a socially efficient network is stable, i.e., the price of stability is 1, and bound the price of anarchy. In the context of facility location games, we also bound the quality of solutions obtained after sufficiently long selfish play without assuming that players have yet reached an equilibrium. As we have seen in part 1 of this book, equilibrium solutions may be hard to find. Chapter 2, and the natural game play may not converge to an equilibrium. Chapter 4, thus it is often useful to evaluate the quality of the transient solutions that arise during competitive play. The facility location game considered in this section is one of the few classes of games for which this strong type of bound is known.